Ever try to teach a computer to see, like, tell the difference between a cat and a dog, from a photo? It's wild.
Yeah.
Turns out it's not as easy as just, like, showing it a million pictures. It's more like, I don't know. It's like trying to teach it a whole new language.
Yeah,
But
exactly.
this language is all about, like, shapes and edges and patterns, all those things hidden in the pixels. And that's where our deep dive today comes in. We're going to crack open this book I found, Deep Learning with PyTorch Step-by-Step. We're going to use it to explore this whole world of feature spaces and activation functions.
The tools that these neural networks use.
Yeah, the tools they use to kind of make sense of the world, just like we do.
Right.
So imagine you've got this big pile of marbles, right? Some are blue, some are red, all jumbled up. And your only tool is a single straight line to divide them. Think you could do it?
It depends.
It depends, right? Like, what if they're scattered in a way that a straight line just won't cut it?
That's where this idea of feature space comes in. It sounds kind of sci-fi.
Okay, yeah, feature space. It does sound kind of Star Trek-y, doesn't it?
Yeah.
So break it down for us. What is this feature space thing?
Well, at its core, it's actually pretty simple. Imagine a map, but instead of cities and towns, we're mapping out the important qualities of our data.
Interesting.
Let's stick with your customer example. Say you're a business trying to understand your customer base. Each customer, then, would be like a point on this map.
Okay, I'm with you so far.
And the landmarks on our customer map would be things like maybe age is one axis and income is another.
Oh, I see.
So each customer is plotted based on those two features. That would be a two-dimensional feature space.
Got it.
But here's the cool part. We can add more dimensions. We can have things like purchase history or website clicks, even social media activity.
Oh, wow.
The more we add, the more dimensions our map has.
So we're talking about a map with like a zillion different directions. That's a lot to wrap your head around. And we can't exactly draw a line on a piece of paper anymore, can we?
Exactly. You got it. That's where this idea of a hyperplane comes in. You see, in a 2D feature space, you separate data points with a line. In 3D, you'd use a plane.
Right.
But when we get more dimensions than we can even visualize, like that dividing thing, that's the hyperplane. Essentially, it's this multi-dimensional slice through our data. And what's wild is that neural networks are really good at finding those perfect slices, even in spaces we can't even picture.
So a hyperplane is like a magic sheet that can cut through our data cloud in a zillion directions at once.
That's a great way to put it. And what's even more interesting is that by shifting our perspective to this higher dimensional feature space, neural networks can uncover these really cool relationships and patterns that would have been totally invisible to us in the original data.
Okay, this is already blowing my mind, and we're just getting started. So we've plotted our data in feature space. We've got our multi-dimensional slicer. Now, how does the neural network actually go about finding the perfect cut? The one that separates our cats from our dogs or our blue marbles from our red marbles.
That's where things get even more interesting. We need to tackle the challenge of data that's not easily separable with a single straight cut.
You mean like if our marbles aren't separated by a clean line, but all mixed up in a weird shape?
Exactly. Imagine those red and blue marbles, but instead of a neat line, they're like, all swirled together, like two of those,
Slinkies?
Yeah, two slinkies all tangled up.
Yeah.
A straight line just wouldn't work there, right?
No, you'd end up with like a bunch of purple marbles. Not exactly helpful.
Exactly. And this is where neural networks get really cool. They can actually transform feature space itself.
Whoa.
Yeah, it's like finding a new perspective.
Okay.
A way to untangle those slinkies without even touching them.
Okay, now you're really making me picture Slinkies doing yoga or something.
Yeah.
But how do you actually transform feature space? I mean, how does a neural network DO that?
Through these things called hidden layers, and those affine transformations we talked about a little bit earlier.
Right.
These hidden layers are like, imagine a series of lenses, and each lens kind of shifts and reshapes how the data's seen.
So it's not about changing the data itself, but changing how the neural network sees it.
You got it.
Wild. Can you give us like an example of what one of these affine transformations would look like in action?
Of course. So remember those tangled up marbles?
The slinky marbles. Yeah.
An affine transformation might be like rotating the table they're sitting on.
Okay.
So what looks all mixed up from one angle, if you just like turn the table,
Yeah.
suddenly it's easy to separate with a single line from another angle.
Oh, so it's like finding that one weird angle where the light hits just right and you can suddenly see a path through all the clutter.
Exactly. You got it. These transformations can involve, rotations or stretching or squeezing, even shifting the whole data set in space.
Wow.
It's like the neural network is searching for the best way to untangle those slinkies.
Yeah.
The perspective that makes the solution obvious.
This is incredible. It's like giving the neural network X-ray vision or something, letting it see these patterns and relationships that we would never see.
That's a great way to put it. By transforming feature space, neural networks can unlock all this insight that would be totally impossible to find otherwise.
Okay, so we've stretched and turned our data into this new perspective. But how does the neural network actually draw that dividing line in this new space?
That, my friend, is where the activation functions come into play.
Okay.
They're the artists of the neural network.
Right.
They take that transformed data and then they use it to paint those intricate decision boundaries.
Okay, tell me more about these artistic activation functions then.
Yeah.
Okay, tell me more about these artistic activation functions then.
So we talked about those hyperplanes, right? Slicing through our feature space.
Right, yeah.
Well, activation functions, they're what let those slices become curves or bends or like all sorts of interesting shapes.
So instead of just like a straight line cut, we're talking about a more, more flexible approach.
Exactly. It's like, how do I put it? Imagine trying to cut a shape, right? You could use scissors or you could like mold it out of clay.
Oh, okay, I see what you're saying.
Yeah, so how do these activation functions actually, how do they work?
Yeah, do they get to just like pick their favorite shape or what?
Well, think of it this way. Each activation function is basically a mathematical formula, right?
Okay.
And it takes the data that's been transformed and spits out a new value, and that shapes the decision boundary. And just like, you have different tools for different jobs.
Okay.
We have a bunch of different activation functions to choose from.
So walk me through some of these artistic tools then. What can they do?
One of the classic ones is called the sigmoid function. It's this smooth S shape, and it's great for when you need a gradual transition between, two categories, like if you're trying to predict will something happen or not, like a probability.
So more of a soft blend than a hard line.
Exactly. Then you've got another one called the hyperbolic tangent, which it's kind of similar to the sigmoid, but it has like a wider range.
Okay.
It's more sensitive to subtle changes in the data.
Gotcha.
And then, of course, you can't forget about the ReLU function. This one's cool.
So ReLU, right?
Yeah, it's like, imagine drawing a line, but with a really sharp corner. It creates these like on or off regions in the feature space.
Interesting. And what about that pre-LU thing we talked about before? The one that was like the origami master or whatever.
Yes, the parametric ReLU. That one's cool because, okay, so the regular ReLU, that has a fixed corner, right?
Yeah.
The pre-ReLU can actually learn the best angle for that bend, like while it's learning.
Whoa.
Yeah, so it's super flexible and can really adapt to whatever data you throw at it.
So we're basically giving these neural networks the tools to kind of like build their own understanding of the world.
That's a great way to put it. And if you think about it, I mean, all the data we feed these algorithms, it's already so complex, right?
Yeah, definitely.
So like, what does that tell us about the real world? Our world. It makes you wonder how complex it really is.
It's got to be way more complicated than we can even imagine.
Exactly. I mean, who knows what we'll discover, right?
It's pretty mind-blowing when you think about it.
Definitely.
Well, we've covered a lot of ground today, from multidimensional maps to
activation functions.
Yeah, activation functions. It's amazing to think that we can like tweak data in ways we can't even picture, and suddenly these patterns just pop out.
It really shows you the power of math and how creative people can be with it.
For sure. And to anyone listening, if you want to, go even deeper, definitely check out Deep Learning with PyTorch Step-by-Step. They have some really cool examples in there, even some animations that really bring this stuff to life.
Definitely worth checking out.
So yeah, the next time you see like your phone recognizing your face or whatever, or Netflix knows exactly what show you want to watch, just remember there's this whole hidden world of feature spaces and
activation functions.
Yeah. Activation functions, all working behind the scenes.
It's really pretty amazing.
Data transforming, dimensions colliding, lines becoming art.
It's wild.
All to help us understand, well, everything.